Hey, Tony.
All right, good morning. I'm Gary, NA6O. So we'll talk about a subject that's near and dear to most of our hearts these days, which is locating and killing receiver interference. Let's see. Are we in something? There we go. So here's what we're going to talk about. Types of noise and interference you might receive, typical noise sources, things that we can actually find. So we're going to learn how to find the noise, where it's coming from. Talk about mitigation, what you can do about those noise sources. Also how to improve your station so maybe it's more resistant to some noise. Also mention your rights regarding the FCC as a licensed amateur and have some references. So I want to mention that this talk focuses on noise that arrives at your receiver. You know, you're getting noise from various places. But a lot of this also kind of works the other direction. You know, your transmitter can interfere with other services like get into somebody else's stereo or something like that. Many of these techniques that we're talking about work in that direction as well. So uh, we won't skip that. Okay, types of noise. Okay, first there's natural. This is a case where natural, being all natural isn't necessarily better. Then there's unintentional emitters, things are supposed to emit, well, not necessarily noise, but they emit something. And then unintentional emitters, which aren't supposed to radiate anything, but they do anyhow. So first we have nature. So these are a lot of things you can't do much about. You have, for instance, lightning. There's lightning all over the world that creates a certain background of noise, especially during the summer in the northern hemisphere. The solar activity, sometimes the sun gets a little upset, radiates a tremendous amount of energy. And anybody who does even VHF, if you point an antenna towards the sun with a very low noise floor system like the moon bounce guys, you point to the sun, you can hear the noise come up. The sun is a big source of wideband radiation. There's a cosmic background, things zipping through the earth and stuff like that. And then there's thermal noise. Every object that's above absolute zero, generates some noise. So you combine all this, and in general, that's that background hiss that you hear. It's everywhere, and there's nothing anybody can do about it. Always, always there. Next is intentional emitters. Okay, this includes all kinds of other transmitters. It can be other hams, it can be something commercial. And this is a case where, for instance, strong signals may overload your receiver. Now when does that occur? Well, at field day, that's a classic thing. You get multiple transmitters in a close location, and one can clobber another. Or if you take your little HT up on top of Mount Diablo, it's not unusual that you're in a intense RF environment. There's lots and lots of big transmitters up there, VHF, UHF, and you're in such close proximity that can overload your receiver or cause some kind of intermod. You'll hear all kinds of bizarre things. Okay, so those are intentional emitters. It's just that you happen to be too close to them. Signals can also intermix. It's called intermodulation. Two frequencies mixed together, you get sums, differences between them, and those can incidentally create energy that's maybe in the ham band. Not probably doesn't radiate too far, but if you're again in close proximity, all these things will combine and generate little carriers and noise and things like that you don't expect. Now, the good thing about intentional emitters is that these are licensed. These things FCC regulated. They have a responsible person or corporation, whatever it is, that takes care of that equipment. For instance, a commercial broadcast, they have to undergo proof of performance every year to make sure their transmitters are clean and things like that. We as hams, our transmitters have to be clean, and we as station owners have to be responsive if we find that we are interfering with somebody else. And if you're doing a field day operation, well, you work with your buddies and you work to mitigate that interference. There's various techniques you can use there. So all this stuff is kind of negotiable. So those are intentional emitters. The bigger problem is unintentional emitters. Okay, this is all kinds of things, any kind of electrical device. It's not designed to be a transmitter, but it becomes a transmitter for various reasons. So here's some pictures of some of the devices I personally have had to deal with. We're talking about, here's a guy with an arc welder, a problem with a PG&E power line, a cracked insulator, uh, a plasma TV, ignition noise, all kinds of switching power supplies, which is the biggest thing we have these days. I had a bad street light in front of the house that's flickering on and off, all kinds of things like this. And each one of these can generate, some kind of an RF fingerprint over some range of the spectrum. And if it falls in the amateur bands, you're going to know about it. So the first thing we have to do is find out a way to, you know, try to track these things down. So I have this noise. Okay, so what do I do about it? The first thing is to get some information about it and then try to locate it. So we'll talk about spectral fingerprinting, getting a signature of it, going through some procedures like powering everything down until it goes away. We do some radio direction finding, and there's also incidentally ultrasonic detection, but that's only for arcing power lines. So the first thing is to get these fingerprints. Okay, I want to know what's the signature of the signal. If I don't have it positively identified, how will I know that I've fixed it? I'm looking for some kind of a signal. Then I make a change and say, oh, that signal is now gone. So it's very important, like to keep a log. I'd have a station log, my station, that just tracks all the RF interference. I look at my noise floor, my S meter readings in different bands, same conditions every time, just to see if it's changed. So first thing is tune around. Okay, what frequencies does this occur on? Is it periodic, like every 30 kilohertz across the band, as an example? Um, is it everywhere, just humming and buzzing absolutely everywhere? Is it on at certain times of day or night? Hey, if it's only on in cold weather, maybe it's a heating system. If it's only on in the evening, maybe it's somebody's lights, so forth. So that might give you some suspicion what it might be. What does it sound like? Just sound like 60 hertz, 120 hertz hum and buzz, just a gentle buzz going on. Sometimes it sounds like video. That's the plasma TV that's actually radiating video signals. Pretty wild. It can be impulses. If you hear voices, I hear voices all the time. I forgot my tinfoil hat. If it sounds like voices, it could even be something like a broadcast station that for one reason or other has leaked into your system. You can record the audio. You can ask others for identification. There's a number of RFI groups, like groups.io. There's a new group there called RFI EMI on groups.io that just got started recently. That was very accessible, and people on there can give advice. ARRL actually has some sounds of RFI, and they have waveforms and things like that. Knowing, I mean, it helps to know a little about it, but mostly is to get that fingerprint, get something down. If you have a waterfall display on your on a software-defined radio, this is a really good fingerprint. Measure the amplitude and frequency. You can see dynamic signals. They're, in a waterfall display, they're moving around in frequency, changing intensity over time. And again, you compare before and after mitigation and write this stuff down, take screenshots, whatever you need to do. So this is a battery tender, one of those little things that keeps the battery float charged. And this was in the house right behind Roberto, K6KM. Hello, Roberto. He's waiting for the North American QSO Party RIDI, which starts at 10 o'clock. So he's listening to this right now. So one of the first things to do is find out, is it my house? Am I the problem that's getting into my radio? That's easy to fix because I own it. So start with your own house. So start by unplugging everything, one thing at a time or whatever you want to do. Even better, turn off breakers. You can start, turn the whole house off and just run your radio on a battery. Again, more of these problems are in the HF bands, up to 30, 50 megahertz, something like that. But once in a while, you have stuff that gets into VHF. So even your little HT may be affected by some noise sources. In any case, you turn off breakers, and suddenly you find out, oh, I turned this breaker off, the noise went away. Well, what's on that circuit? Let's go look. Let's see what's on that circuit. Oh, it's this new gadget I bought. It's plugged in behind the TV set or something. Who knows? And go find that widget. Ah, this is a smoking gun. I've got this device here. This seems to be causing my noise. If it's unplugged, the noise goes away. Now you can do the same thing with neighbors. Okay, I've proven my house is okay. Noise is still there. And we'll talk about direction finding, but if it's in your neighbor's house, hopefully you're friendly with your neighbors. Otherwise, you'll get absolutely nowhere. But it's the same thing. So direction finding. Now, this is a case where, okay, it's not my house. I need to walk around the neighborhood. So I would go around with a clipboard with a Google map of my block and a pencil. I'm kind of walking around like an idiot. And I feel like, what the hell is wrong with this guy? But it does work. And so we do direction finding. Now, this can be on any possible band. It can be medium frequencies, literally an AM radio. Um, More often, it's you want to look at the frequencies that you know are interfering with your station. If I know that on 40 meters I have a problem, I would like to listen to 40 meters as I walk around. Uh, VHF and UHF are actually very good detectors for arcs. So if you have above ground power lines and you suspect it could be a PG&E problem, which tends to be this broadband 120 hertz buzz everywhere on many, many bands, if it's actually an arc, arcs emit energy at all frequencies, including audio, on up to light. If you think about it, it's truly the ultimate emitter. So an arc, you can see it, you can hear it, and it radiates at all frequencies. So different antennas you might use. The VHF Yagis. Um, some of you guys who've done like the satellites, they have these little cross pole dual band Yagis. It's 2 meters and 70 centimeters. The handheld ones. Who makes those things?
Arrow.
Arrow, yeah, those arrow antennas are really nice. Handheld, pretty light, and you can plug it into your HT. Put your HT in AM mode. This is all amplitude modulated crap. FM, you may not hear it. Maybe you will, but it's more AM. And that little arrow antenna, if it's an arc specifically, you can really find it. You can really nail it with a VHF or UHF antenna. This is a loop antenna that I use, and we'll talk more about this in a second. These loop antennas are very directional. You get a null looking through the loop and a peak along the edge of the loop. So I can turn this and hear the signal go up and down. Of course, I can't tell, is it behind me or in front of me? And that's the reason you have to like walk around the block and draw lines, and maybe they'll intersect at the guy's garage behind me who had a defective welder. There was something wrong. The electrical system was welder, which is actually hot. He said, well, you might want to fix that before it burns your garage down. Sometimes they're appreciative. You tell them, I hear an electrical noise. It could be a fire hazard. Now you got their attention. So yeah, this loop is really a nice thing. This is on my website. I have an RFI page. So the way this works is it's 2 turns of like 12 gauge wire, and that's in series with a tuning capacitor. I have a knob on the top of this thing, a little tuning knob, and you peak it up. You hear the noise get louder when you peak it up. There's a smaller loop in here, which is inductively coupled to that, and that's where the signal is actually picked up. And then this plugs into my little portable shortwave receiver or whatever I happen to have. And they're actually pretty easy to make. I have a couple designs up there. One's even easier than that. Another thing I use is this little guy. This is called an RF sniffer probe. All this is a tiny little coil on the end of a piece of coax. That's all it is. A little coil wound around my little finger, soldered on the end of the coax. And this is when I'm trying to find noise that's on, maybe it's a bunch of cables. There's some source. I'm trying to localize it, get very, very close to it, or it's in something I've built. I don't know, whatever it happens to be. So this just probes the magnetic field for noise. It's very broad banded. And again, this can be used with anything from a receiver to a spectrum analyzer. That's a sniffer probe. But the portable antenna is really nice because so you can walk around and get a direction like it's over there, and that's very helpful. So what can we use to listen? Well, here's my little Texan 660. Bought it used on eBay, $100, something like that. Covers medium wave, all through the HF bands. Also does VHF. Primarily, I use it for shortwave. It's got a jack here I can plug my antenna into. Simple receiver like this works just great. Little spectrum analyzer, tiny SA, they're $120, something like that. It's a real spectrum analyzer. It's actually quite sensitive. Same thing. That can be used with this antenna or any other kind of antenna. And then you get this nice spectrum analysis. You get a waterfall display. They're very powerful, and again, not very expensive. And of course, your HT or any other radio, that can work pretty good. You do need to put it in AM mode. SSB is okay, AM is better, just because our signals are all amplitude modulated here. My all-time favorite, this is very, very nice, the IC705. It's kind of expensive, but once you buy it, you have a real radio. I mean, it's a QRP radio, but it covers all bands and all modes from, 160 meters through 70 centimeters. It's very lightweight, battery powered and stuff. Has this fantastic display, great audio. The thing even has an audio oscilloscope. You can look at the audio waveform on this thing. It's fantastic. So this one, I can have my HF loop plugged into it to get kind of a rough idea. And then I was looking for power line noise. Then I plug in the aero antenna, and I'm looking on 2 meters or 70 centimeters to try to find, broken insulators, that sort of thing. Fantastic radio for this purpose. So now you found it. Okay, I found noise. There's something in this guy's house or whatever it is. Or maybe you've located some kind of a power supply. You've looked some object, some device, whatever it is. What do you do about it? Well, it's the obvious list. The first thing is you can remove the offending device. Maybe you can just get rid of it. You don't need it. You can turn it off when you're operating. If it's yours, at least you can turn it off. I have some noisy light. I had noisy lights in my shop. Well, I don't just turn the lights off. Use a different light that's not so noisy. Replace the device with something less noisy. Replace a switching power supply with a linear power supply, something like that. There may be a substitution. Or the really crappy charger that's on somebody's laptop, get the genuine Dell, HP, Apple genuine charger. It's probably a lot quieter. Then we can do what we call choking or filtering, some kind of shielding to reduce the radiation. That's what we're going to do. Do have a lot of details in that coming up. And then finally, try to make your station somewhat more resistant to the interference. So we'll do some examples. First thing I want to talk about is, why are these devices radiating and how are things susceptible? What's going on there? Well, the answer is this is what we call primarily common mode current. Now, normal mode current, for instance, I have a piece of coax here. I got a trusty piece of coax. The normal current is flowing on the inside of the coax. Or if I have a pair of wires, you have your plus and minus, and the current's flowing in a loop, goes out in one wire and out the other. That's the normal current, this normal signal current or power. Common mode is the same signal on all conductors. In the case of two wires, imagine them both being plus or both being minus at the same time. So it's common to both conductors. On coax, it's running on the outside of the shield. Because of skin effect, you have your normal signal on the inside, which doesn't penetrate through the shield, and you have noise on the outside of the coax, which also doesn't penetrate through the shield, but it does ride on the shield. So that's what we call common mode. Now, if you have a device, as I have in the picture here, that's a noise generator, that's producing some kind of noise current, it's connected to what? Wires coming out of that device. Well, those wires, that's an antenna. And if it happens to be the power cord, that antenna extends not just the power cord, but into what? The wiring system in the facility. So now all of a sudden you have an antenna that's, well, sort of infinitely long. Well, really long antennas make really good radiators, especially at low frequencies. So, if current in the wire, that means there's electromagnetic radiation. If it's a long wire, it's a better antenna. It's going to, be more likely to radiate and do some harm. The converse is true. That is, if there's a noise source coming in to my receive coax, for instance, or some wire that's connected to my receiver, that noise is picked up, again, common mode, and coupled into my equipment. So it works both ways, noise coming in or noise, going out of a device. So what do you do? Okay, the first thing is just to try to reduce the common mode current. If you reduce the current, that means there's less noise signal. So the way that's done is by inserting some kind of a high impedance. The high impedance, that reduces the current. If you reduce the current, you reduce the amount of signal. So what our intent is to reduce what we call the common mode current without affecting the normal mode current. You can twist wires. That's another way to, keep it all balanced, things like that, so it doesn't turn into a normal mode signal. And the way we do this is with a thing called choke. Choke classically is a term for an inductor. Inductors have a high impedance. As frequency goes up, the impedance goes up, right? That's a choke. So we insert a choke that only acts on the common mode current. Doesn't affect the signal at all. It's only this common mode current that's carrying the interference. So how do you make a choke? Well, the simplest way is you can take wire and just make a coil out of it. A better way is to use what we call a ferrite core. Here's a ferrite core. I have a whole box of them here. What this does is this increases what we call the magnetic permeability. Air has a permeability of 1. This particular material here has a permeability around 2,000. So this is, several thousand times more effective than air. So if I wind wire around this, it focuses the magnetic field in the core. So that way I get, more inductance, for per unit length of wire if I wrap it around a core. These cores also are lossy. So that's good. Well, what happens to this noise signal? Maybe I'm trying to stop it or whatever. I can actually absorb it and turn it into heat. That way, I'm not just reflecting it somewhere else to re-radiate. No, I'm going to dissipate it. I'm actually going to, dispose of it. So there's all kinds of ways you can apply these. The classic way is to uh, wind, and turns are very important. Inductance goes as turns squared. So if I double the turns, I got 4 times the inductance, 4 times the impedance. That's a good thing. So having a single wire go through the toroid, okay, that's something. But especially in the HF bands, the amount of impedance you get is minimal. So what you want to do is wrap it around the toroid as many times as you can, and the inductance and the impedance goes way, way up with a structure like that. There's all kinds of different forms of the ferrite. This is a ring. We also have various clamp-ons, little tiny ones. Here's a gigantic clamp-on. They can be used for different purposes. Little tiny ones I use on power supplies. Here's an example. This is a power supply. This has a small one on this cord and a larger one on this cord. But same thing, lots of turns. It's the turns that are your friend. When you're dealing with VHF and UHF, you don't really need the turns anymore. The ferrite itself has sufficient impedance to do a decent job. So for instance, on 6 meters, 50 megahertz, this is called a bead balun. These are just gigantic ferrite beads on the outside of the coax. And then on something like 6 meters, about a half dozen of these beads are reasonably effective. Same for VHF, UHF, microwave, whatever it is. You always see cables that have a little, look like the snake that swallowed something. It's got a little bulge. Well, that's a chunk of ferrite. And that's primarily for really, really high frequencies, hundreds, thousands of megahertz. Um, so yeah, ferrite is your friend. Here's just a quick plot. This is impedance versus frequency. So this is a choke balun. We commonly call these baluns balanced to unbalanced. This is a device that's used at the feed point of, for instance, a dipole. So you bring your coax up the dipole, the inner conductor goes to one side, the shield goes to the other side, right? Okay, that's the classic connection. Well, there's one problem though, is that the outside of the shield also goes to one side of the antenna. And the outside of the shield is the one I'm saying has the common mode current, the noise current on it. So the noise current goes up the coax, onto the wire, down the inside of the coax to your receiver. So if you have a choke, that noise current is stopped. It can't get to your antenna. That's one of the primary ways of reducing the noise susceptibility of any receive antenna, is having this kind of, actually, it's a common mode choke. It also services as this balanced to unbalanced or balun purpose. So this is one in this little picture. It's wound with what's called RG400 coax. It's the size of RG58, but it's all Teflon. It's wrapped around there about a dozen times and has this very high impedance. Even on the low bands, like an 80 meters, 4 megahertz, this thing's, this is over 6,000 ohms. So, that's a really, really nice high impedance compared to our sort of 50 ohm systems. And the reduction of noise current is substantial when you have an effective choke like that. So now we're going to have a little demonstration. John, I'll need your services up here. So we're going to try something here with a little, with my noise finding rig. So,
stay your way. Keep talking. You're fine.
all right. So this is my typical walk around the neighborhood, go find the noise thing, right? So I got this radio here, and hearing all kinds of noise. Now I can actually start search for noise right now. For instance, oh, there's a computer. Yeah, there's a computer in front of me. Guess what? It radiates noise. Now, everything radiates some noise. The question is how much and how far away are my antennas? Now, if my antenna is 100 feet over there, this little bit of noise here probably isn't too much of a concern. 1 over r squared. You get farther away, the noise is, just diminishes. But sometimes you find noise that you can hear from, if you will, down the block that you pick up. Something that's really, really loud. It's a very powerful unintentional emitter. So that's the kind of thing we're looking for. So yeah, this computer's radiating something, but I wouldn't be too afraid of it because as soon as I get 3 feet away from it, I can't hear it anymore. So that's not too bad. But I have something that's really bad. So I'm going to hand this to John. He's going to be my search guy.
Try and hold the mic next to the speaker here.
Yeah, once we get cranked up. So I have here lithium-ion battery charger from Rigid for my little cordless drill. It's a wonderful thing. Charges batteries just great. But it has a problem, don't you know? Okay, John, let's see. Let me make sure the thing is peaked up. I think it is. Peek up the antenna here. Okay, it's got a little tuning knob, peaks it up. All right, there. That's good. All right. So we're going to plug this little darling in and prepare to start the music. Takes a second for it to initialize. Nice, huh? Mm-hmm. That's on AM, so it's fully modulated. What do you got on your S meter there, John?
S4.
S4, that sounds pretty good. Turn the antenna, see what happens. Does it go down?
Went down to S2.
There you go. Okay, so looking through the loop is a null. That's what we want. And as he rotates it towards me into my plane, the noise goes up to S4, okay? So what can we do about it? Well, we can unplug it, replace it with a charger that doesn't make noise. We can try to mitigate it. So I have a large clamp on, big chunk of toroid here. And here I have actually 6 turns of the power cord here. So I take my chunk of toroid, of ferrite, and I kind of pack the turns in there. Now I haven't closed the toroid, so it hasn't closed its magnetic circuit. Okay, here we go. 3, 2, 1. Ah! All right. So how about that? I'll take it off. It's back. Now, what if I don't have any turns for whatever reason? I only have one pass through the core. Let's see what this does. Didn't work. Well, 6 turns, that's what, 36 times the amount of impedance, right? So that's the magic of having turns through a core, depending on the frequency. If this is a VHF problem, a single turn may be enough, but yeah. Oh, that's so much better. But walk closer to it, John. See what happens. It's still there. It's still there. You haven't made it go away. You simply reduced it. So it's only when it's charging that the thing makes noise, as it turns out. Some things just make noise as long as they're plugged in. So yeah, okay, we're done. Yeah, this is exactly the problem with countless devices. These things are absolutely everywhere. We have all kinds of switching power supplies. This battery charger is a classic. That's what it is, a switching power supply that generates energy over a very broad spectrum. And if this is anywhere near my station, I mean, that's the kind of thing you can hear from a block away. So all you need is one neighbor with a bank of battery chargers in his garage. And every Saturday he finishes, doing his chores, plugs in all his batteries, and your noise floor goes up. It's this chorus of all these different devices. But you can see that antenna was directional enough, you could say, is it this way or that way? So at least you got a vector towards it. If you walk around the room, you'd have vectors that are all kind of pointing to me here with this noisy power supply. And you do the same thing walking around the block. It does help, as I said, to know kind of what frequency it's on, where the problem is, and what it sounds like. There's a particular sound I've been looking for. This one's very distinctive. A waterfall display would show all kinds of patterns, and you would, be able to dynamically see what happens.
Sure. What frequency were you listening on the?
That was 7 megahertz. Yeah, 40 meters. And the lower frequencies tend to be a sewer for RFI. The lower you go, the worse it gets. 80 meters, 160 is horrendous for noise in an urban environment. Again, mostly you guys operating VHF are very lucky because a lot of this energy just doesn't radiate very well. It's in some ways it's more easily suppressed. These things just don't produce that much energy way up at the on 2 meters, that kind of stuff. But sometimes they do, and you'd be knocked off the air. So here we are. Let's talk about different sources. Wall warts. Okay, this is one, and what do you do about it? Well, the first thing you can do is replace a switching supply with a linear supply. They're kind of hard to find. These things started showing up in the 1990s, and because they're so efficient, these are 95% efficient or something like that. They're lightweight. They have a lot of advantages. But if they aren't properly engineered from a standpoint we call electromagnetic compatibility, if they don't put the components in, the filtering components on all the connections, input and output, as many connections you have, each connection has to have filtering on it in the device. If they do that right, it'll be quiet. If they don't, well, like this little piece of crap, well, guess what? It radiates a lot. So this one had to be choked on both cables. Same thing, lots of turns on a suitable core. So that's our common mode chokes. The other way, another thing you can also do, especially with little wall warts, is you can plug them into a filtered outlet strip. Now that could be an outlet strip where the power cord on the outlet strip has a choke on it. Or you could find a commercial one. I think I have a picture of one of those, a commercial one that does some filtering. At least that takes care of the AC line side of the problem, but the DC cord can also be radiating. And you have no choice but to put a choke on that or, again, replace the supply. Mm-hmm. Yeah, that's the best solution. So LED lights, of course, are taking over the universe. Some are absolutely horrible. Fixtures in particular can be really bad. Every LED, of course, requires DC to power the LED itself. Well, we have 120 volt AC, so there's some kind of a power converter, whatever it may be, and it turns your 120 AC into some kind of voltage DC to drive the LEDs, and that's the problem, is that little power supply. Now, if you buy a fixture, maybe it's one that light goes in the ceiling, some of these things, who knows what. That power supply is built in, and there's not much you can do about it. You can put a choke on the AC line side of it. I've got lots of stories about that, and that can help significantly. The bulbs, the screw-in bulbs, the 100-watt light bulbs, those sorts of things, those are very good though. Those are very, very quiet. I've tested a number of those. I've tested, for instance, GE and Fight as examples. Very quiet. And of course, if it's noisy, you can always get it. One that's not noisy, you can screw that in instead. So yeah, the screw-in bulbs are fine. And on my website, I have actual formal testing that I do for noise. And you'll see all kinds of LED lights, among other things. Some are properly tested. They've gone through FCC certification. They left the filtering components in when they manufactured it. Quite often, they design it, build it, test it, and then throw away all those components that cost too much. They don't affect the operation of the thing. They just affect the noise. And you'll find, you look inside, here's a power supply, and there's a circuit board, and there's a whole bunch of missing components in the circuit board. That's the filter components. They didn't put them in. That's very, very common in the industry. Mobile inverters, you want 120 volts off your 12-volt car. Well, a lot of these inverters are very noisy, and on my website I have a list of some things that are quieter. But this is the kind of thing you have to go through to get rid of the noise from, in this case, an inverter. It's just another switching supply. UPSs. Many of us have uninterruptible power supplies. Here's an example one that's very good from CyberPower. These are known to be quiet. They did the right thing. It's properly engineered. Everything generates some noise, but once again, this one will not cause you problems. Here's Ian holding the biggest chokes I've ever wound. So that's 2 4-inch toroids. These are really expensive. Wound with number 4 cable to it's 75 amp power poles on the thing, on the charging circuit of the big ups that's right next to our station up on Sonoma Ridge. We told the property owner, don't do this. Don't install this thing. It's going to generate noise. Well, he installed it anyway. So here's, this, I call this my $150, choke here. And that's what it took to knock it down to where we still hear it. And you still hear the thing buzzing away. But a good ups is, for instance, this one is quite clean. But you don't know until you try. So, I've inspected a number of these, and here's one that's good. Defective power strip. Some of these power strips, well, some of them are really poorly built. You look at them, they'll barely retain the plug when you plug it in. Little plastic things, they almost fall apart when you use them. Those are just plain unsafe. But some of them have all this electronic crap. They have LEDs on them. Oh, there was a pulse, or all this kind of stuff. Well, it turns out those components can suffer partial failures over periods of time. Metal oxide varistors, they receive damage every time there's an impulse that they absorb. So some of these things can turn into noise generators. I found a couple of them up at N6RO that were that way. So if it looks like it's really well built, it probably is. Have good connections on them, that kind of stuff. These things from Weber, it's a steel enclosure. It has real outlets on it. There's no electronics, that kind of stuff. If I need filtering, that kind of stuff, I'll put my own filters on the outside, or put a choke on the cable. Ethernet cables. 10100 Ethernet will radiate on a few bands. The main one is at 14.030, 14.030. Put your rig there, and you'll hear these little twiddles right around 14.030. Contesters know never to set up shop running, operating on 14.030, because some stations have really bad Ethernet interference. So this is how you choke an Ethernet cable, about 12 turns on a X31 core here. And these have to be applied sometimes at both ends of very long Ethernet cables. If you go to Gig-E, gigabit Ethernet radiates far less noise, as it turns out. Wi-Fi, of course, doesn't radiate anything in ham bands. There's all kinds of different ferrites, different mixes and things like that. This mix is called 31 from a company called Ferrite. They're the primary maker of ferrite these days. There's like micrometals and stuff. This one is optimized through the HF bands just up into VHF. It's providing pretty much the best characteristics, the most loss, which is what we're looking for, and decent amount of inductance. I should probably do a talk someday on ferrites and chokes and balance, stuff like that. It's a really good topic. And this is typical if you buy a commercial balun for an antenna, for instance, from Balun Designs. That's what's inside. It's just like that. Plasma TV. Thankfully, they're going away. It radiates right off the screen, and there's nothing you can do about it. Yeah. But yeah, yeah, just encase it. Yeah. Yeah, encase it in copper. No, a bullet through the screen is the only solution. Um, Failing electrical equipment, things that are arcing and sparking. You see a flickering fluorescent lamp, that'll do it. Flickering street lights, yep, city had to fix that. Bad capacitor in the neighbor's AC unit. Every time their AC unit came on, I hear this horrendous noise. I said, that isn't right. So I go over there with my buzzing radio, knock on the guy's door. I said, your air conditioner has a problem. You hear this noise? Go turn your air conditioner off. Noise goes away. Your air conditioner has an electrical fault. Something's going to fail, and it's a fire hazard. Remember that term, fire hazard. You'll always get their attention, say, oh, yeah, I better take care of that. So sure enough, the guy comes, swaps out charges you $600 to replace the $15 capacitor, and the problem goes away. I also want to mention the certification that goes on all electronic devices. If you look at it, you always see this FCC Part 15, FCC Part 15. What that addresses is primarily, well, it's both intentional and unintentional emitters. That's all of our electronic gadgets, everything from radios to computers, power supplies, lighting equipment, everything kind of falls under Part 15. And devices are supposed to be certified at a testing lab that they meet specifications, which limits the amount that the things can radiate, is what it amounts to. Well, there's also there's a Part 15 class A and B. B is consumer. It's a lower level. It's a more stringent requirement. Class B, consumer. So you'll see on a device like an UPS. I'm looking at UPS, and CyberPower says FCC Part 15 Class B. It's meant for consumer use. Other things are Class A, which is commercial, which is about 10, 15 dB worse in terms of its spec. And the switching ballasts and fluorescent lights are famous for being Class A. In fact, Home Depot got in all kinds of trouble for selling a bunch of Class A ballasts in their products. And said, no, you're a consumer outlet. You can't sell Class A rated electrical equipment. So they had to cut those suppliers off or get different gear. So look for Part 15 Class B certification. That's better. It still allows quite a bit of noise, though. It doesn't mean no noise. It means it's hopefully not too bad. Solar. So solar is a big thing these days, of course, and you never know what a solar system is going to do. You just never know. There was a QST article a while back. This company, Solar Edge, they've actually been pretty responsive. Got one next door. Power optimizers, panel optimizers, they call them, are microinverters. This is an inverter. Every panel has its own inverter, and it generates, it produces, the necessary, usually DC voltage going to the main inverter, things like that. It does what it does. But the idea is you have many switching power supplies, one on every single solar panel, and each one of those is potentially, guess what, another noise generator, another noise emitter. And depending on its design, how good its filtering is, how it's installed, that is, how did they run the cabling? All these things matter. It all matters. And like Solar Edge has very specific installation requirements, thou shalt twist these wires. You have to run them in this manner and so forth that will minimize the RFI if it's properly installed. Some equipment is known to be very good. These companies, Enphase, that's very widely available. You can look for all kinds of solar suppliers that sell Enphase. Enphase is very good. Again, properly installed. You probably won't have any noise problems with Enphase. These other companies, Fronius and SMA, are made in Europe, but they're available in the US too. And you never know. You just never know. Hopefully, the next solar system that's installed in your neighborhood is farther down the block. If it's far enough away from your antennas, you probably won't care. If it's right next door, maybe it'll be a problem. And these problems can be very difficult and expensive to fix. High voltage power lines. It's never the transformer, by the way. No, there's a transformer. It's not the transformer. It's never the transformer. It's always an insulator or a bad connection. Loose hardware is very common. Weather and that kind of stuff loosens hardware over time, and you get arcing. And the arcing may come and go with the weather, especially with rain, that sort of stuff. Direction finding, you start in the HF bands. The problem is the energy in the power lines, the antenna is tremendously long. And on the HF bands, you'll find a peak null, peak null, peak null. You're driving for miles, peak null as you're driving along. You can't find it. So it's almost hopeless. So that's where the VHF and UHF comes in. You basically walk by and interrogate every pole in the neighborhood and try to find, a hot one. And change the polarization on the antenna when you're doing this. Sometimes it's strongly polarized. Then you write down the pole number, report it to PG&E. They have an online thing you can report it. I think there's a phone number. We have contacts in PG&E though. Locally we have a brother-in-law of another guy who has connections, and sometimes we can, sneak in the back door, which helps. You have to keep bugging them, document everything. If they don't respond, then you report them to the Public Utilities Commission, the FCC, work through ARRL. And usually after 1 to 2 years, you can usually get PG&E to come out and look at the problem. And once the guy gets on it, they will fix it. They will fix it. The guy comes out with his radar engineer's receiver and he goes around and says, oh yeah, it's a bad one. They'll send a guy up on a bucket truck. He'll look, oh yeah, we got some old hardware up here. This needs to be replaced. And they'll send a crew out to fix the problem. They will fix it eventually. We've had 100% success on identified problems.
Almost fire hazard.
And tell them it's a fire hazard. I've detected arcing on one of your poles. It could be a fire hazard. Yes, works every time. Filtering the AC lines themselves. This is more a thing where you're trying to solve a noise problem because of wall warts and things like that. Just putting a filter on the AC line coming into your house will probably do absolutely nothing. Forget it. It won't make any difference because you're surrounded by other AC line feeds and things like that. What it is useful for is what I call like a wall wart island. So that's where a filter is installed in an outlet system. That way the wall warts, their noise doesn't get conducted into the AC line to radiate, and you only have to worry about their little DC wire, and you put the little tiny toroid on that. Now there's commercial versions of this. Here's one. Triplite makes a thing. These are fairly expensive. These are around $100 just for a little 4-outlet unit. Now that one does have a proper EMI RFI filter built into it. Most of them are just surge protectors, just got a metal oxide varistor, not much more in it that you pay all kinds of money for. Once again, it still contains a bunch of electronic crap, which is completely unnecessary. It's absolutely useless. It's just another potential failure and another thing that can generate noise. Along with trying to filter out the noise. No, I'm going to put in some components that can generate noise. Good idea. So sometimes this needs, a choke on the power cord to finish the filtering job. So next thing you can do is reduce your station's susceptibility to this noise. So the first thing I mentioned is a common mode choke or a balun on the transmission line. So you start with this good choke at the feed point of your Yagi, your dipole, your vertical, whatever it is, the choke right there. That will prevent noise that's carried on the feed line from getting onto the antenna and then back into your receiver. That's one of the reasons to have a choke out there. You can choke other conductors. There can be other things that are picking up, the Ethernet cable, you put a choke on the Ethernet cable. Sometimes you have problems in your station RF getting into your shack. A lot of that's cured by having one of these really good chokes on every antenna. If the RF's getting into the shack, maybe every time you go key down, you have a USB device that disconnects. Well, you put the little choke, small toroid, and you wind your USB cable around it, and you can get rid of that problem there. Now, low noise receiving antennas. This is a really good topic. I'll have some more on this coming up. So as a rule, some antennas are noisier than others, as it turns out. Quite often, the classic backyard vertical, multiband vertical, may be more likely to pick up noise than something like a dipole. A lot of our noise that we have tends to be actually vertically polarized, as it turns out. A dipole may be better If you just want a dedicated receive antenna, and many HF rigs have a receive antenna port on it just for that purpose. You transmit on one port, you could receive on it too. Then it has another port that you can use for just a receive antenna. So you can do something as simple as a low dipole. This can be a dipole laying on the ground. It's not resonant. It doesn't have to be resonant. It doesn't matter. Receive antennas are not high gain. The signal level will be low, but the signal to noise ratio is improved. So there's a variety of low noise receive antennas like that. I had a little wire dipole tacked up about 3 feet off the ground on my back fence. I used that as a receive antenna, and that was much better than the elevated antennas. Your radio every modern radio at least, contains some features for noise reduction. You have a noise blanker, which primarily works against pulsed or repetitive noise. It works actually against a lot of PG&E type of buzzing noise. It has an adjustment on it, how intense its action is. Check with the noise blanker. They have noise reduction, do all kinds of signal processing tricks. And then finally, you can choose a better mode. Let's say here, FT8 is greater than CW, which is greater than SSB. SSB requires quite a bit of bandwidth, and the average power is somewhat low. When you move to CW, that's about a factor of 10 improvement. Go to FT8, that's another factor of 10. So now effectively your station could be 100 times more powerful, if you will, and that works on receive as well. It works both ways, transmit and receive. By going from SSB to FT8, that's like a factor of 100 improvement. So FT8 has been a real blessing for hams with very small stations, high noise levels, and things like that. Common mode chokes, I keep mentioning here. You choke on your coax, a choke to prevent noise getting out of noisy devices. K9YC.com, that's the place to go. He's the god of ferrite chokes. He has some big articles there. This has been widely propagated. It's very well known. He has a cookbook on how to wind a super optimized choke, different trade-offs, things like that. If you want to study it, that's the place to go. Low noise receiving loops. These cover all HF bands. No tuning required. It's not a resonant loop. It's just what they call a shielded loop that then has a low noise amplifier at the base. These are really neat. The one I had was made by Wellbrook. Tony Ammon has it now. I sold it to him. Wellbrook's out of business, unfortunately. But it will null noise, close by noise, like my neighbor's plasma TV, which is why I bought this thing. I put it as close to their plasma TV as I could get it, turned it until I nulled the thing out, and the plasma TV was magically gone. So it really does work that well. And these can be installed they can sit on the ground. They're for distant signals, they're actually omnidirectional. You don't really have to put a rotator on. And there's a couple companies that make them right now. W6LVT and DX Engineering sells one from Pixel Technologies. If you have a resonant loop, like my little noise finding loop's a resonant loop. Resonant loops also are very good as low noise receive antennas. So that can be plugged into that receive jack on your rig. One myth that we need to get rid of: I need a better RF ground to reduce my noise. So this is the concept that driving a ground rod and connecting your station to it will suck away all the evil spirits. They'll just disappear into Mother Earth. Well, no, it probably works the other way actually. So first, the thing that I like to say, there's no such thing as an RF ground beyond the domain of like the ground plane on a circuit board or inside a chassis. That can have an RF ground. As soon as you move some distance, you have wavelength effects. Like a quarter wavelength, a dead short turns into an open on a quarter wavelength. So here I connected it to ground. Ground is 0. Well, a quarter wavelength away, it's an open circuit. You're not connected at all. So this whole business RF ground, it's wavelength, inductance, skin effect. These other things go on, so that no, it has nothing to do with your antenna performance or anything else. You do not need a connection to earth ground for any antenna, period, ever. Except for beverages. A beverage receive antenna actually does use the earth as a conduction path, curiously enough. But one fact is, a connection to earth is necessary for lightning protection, which is blessedly, we don't really have that here. And more often, this connection to Earth may actually make it worse because guess what? It's, yet another antenna, another noise pickup antenna that's connected to your station. So if you have an Earth ground somewhere and you have a noise problem, at least temporarily disconnect it. See what happens. Either it gets better or worse. I can't tell you what. Quite often, it actually makes the problem worse by having the thing hooked up. There's a book on this from ARRL, highly recommended, Grounding and Bonding for the Radio Amateur, all about grounding, bonding, lightning protection. It has all the stuff on chokes. It's all in there. It's a very, very good book. So as a ham, the FCC gives you rights and responsibilities, right? So here's the terms that are written into FCC Part 15, which governs all these devices that may radiate things. So devices that cause harmful interference are at fault, and the operator, the owner, is legally responsible for fixing it. So my neighbor installed 23 new LED lights next door. I have 20 over S9 noise on all bands. That's pretty harmful. I have a nice presentation working with the FCC and ARRL that basically had to go after him and say, you have to fix this because you are interfering with a licensed radio service, which is me. So say he is responsible for fixing it by whatever means. That's the letter of the law. Similarly, devices that can't accept interference from licensed and legally operated services handle the same way. I'm getting into the neighbor's stereo. Okay, that happens. Getting the neighbor's stereo. Technically, it is not my problem. Legally, it is not my problem because that device has to accept interference from a legally operated, proper station. Now, but your responsibility is your transmitter needs to be clean. If I'm generating harmonics to get into the TV and that kind of stuff, I have to fix that. But also as a goodwill gesture, we want to be good neighbors. Promote ham radio as being good, helpful people and that kind of thing. So you really do need to help fix this problem at your neighbor's house, even though legally it's not your responsibility. Morally, it is. All right. And ARRL has lots of resources. They have an RFI handbook and things like that. And they give you all kinds of advice on working with the neighbors to fix these things. List of references here, some very good books and things like that, and some websites, my RFI website. I'll put this presentation up on the groups.io thing, and it's on my website as well. This is another thing I have to write this down. This type 31 ferrite, really, really good stuff here. These are some references of the exact part numbers. There's little 1-inchers, the 2.4-inch. There's a gigantic 4-inch. There's this great big clamp on we were working with. That's some examples. Here's some sources, where to buy them. You always see the ads for Palomar Engineering and Amanon and stuff like that. They're way, way too expensive. You pay anywhere from 2 to almost 10 times the price at some of these sources. So Arrow has really good deals right now and free shipping. So this is another, you don't have to write all this stuff down. It's on the website. So this is the epilogue here. So this is my RFI disaster, the LED light fixtures next door, worked with all the agencies and stuff, tried to fix it. We ended up installing chokes on every one of these light fixtures, huge pain in the ass. Let's say it was a 20 dB solution to a 40 dB problem. Remember, we fixed this with the choke. It was the same thing, LED light, choke on it. Well, yeah, it kind of fixed it. But then remember, John walks towards it and the noise ain't gone. It's not gone. It's just reduced. So yeah, it reduced it, but no, that's it. That's it. It's an ongoing radiating disaster that I can't escape. But when they're gone, the lights are off. It's not too bad. So that was my solution. So that worked out great. Thanks to Ian, W6TCP, we have this really, really nice station to operate at. And that's one way out, but it's an expensive and complicated and rare solution. And that's it. So up here, I have a bunch of these 2.4-inch toroids at a very good price, $5 a piece. These are sort of the universal solution to all these RFI problems. You know, that's my go-to default part, works for just about everything. I also have a few of the big clamp-ons. Those are $20. They're pretty expensive. But these are $5 a piece. It's hard to get them at that price. I just bought 50 of them. I always buy them in big lots because I do a lot of this, as you can imagine. It's my thing these days. I think I spend more time fixing RFI problems than I do operating. So get them while they're hot. Okay, questions?
Microphone here.
Hey, Mr. Microphone.
I was wondering if you could give some guidance on getting solar installed. So some years ago, my wife and I seriously considered installing solar at our residence. And we didn't because it didn't matter what company we were working with or whatever, with one exception, no one would let us talk to an engineer. And so I explained that I have an amateur radio station and well, I wasn't going to let anything get in the way of my operating. And so if they couldn't, give me some assurances, let me talk to an engineer or whatever to understand what they're doing to make sure they're not causing RFI problems, I wasn't going to buy. And so we never did.
Yep.
So, okay.
Yeah, this comes up in the RFI reflectors all the time. The best you can do is have them write into the contract that they will solve any significant RFI problems. And that's the issue is, what's significant. The things you can do, you can possibly ask them to write it into the contract that they will not cause harmful interference, which again, legally that's the problem is you become the owner and the operator. Legally it's your problem to fix it, not theirs, but you can write it in the contract. The other thing is to choose the equipment that's known to be low RFI, like Enphase. If you pick an Enphase system, and even better, one that doesn't use the panel optimizers, just has a central inverter and nothing else, that's more likely to be quiet. And finally, you can say, well, I need to get my antennas as far from that solar equipment as I can. So that's about it. What? Like, the mic back there?
So I think we need to do a before and after background noise measurement as the solar farm on the north side of the freeway is implemented. There'll be 10,000 plus panels up there. So
yeah, those are ARRL has been studying that intensely recently, and they have not found a case yet where significant RFI was detectable when driving past the boundary of any big commercial solar farm. So that bodes well for us. I think it may have to do with, again, the other installation details and equipment they're using and things like that. Everything's in conduit and so forth. So I don't think we have a lot to fear from the massive installations. It's a sloppy home installation that's probably our bigger concern for most of us. And, the one next door.
I had a question about your take on the pin 1 problem and how these RFI issues interact with bad radio designs that couple basically the coax shield to the ground of the RF sensing parts of the radio.
Yeah. Pin 1 problem. So what you're referring to, this goes back to actually audio engineering, what's called an XLR connector, which is a balanced audio connector. This is the ones you find in all the professional microphones. It's got 2 leads for the signal and a ground. So the ground there is the shield on the cable. And what happens is you take that shield, and ideally what you do is take the shield and you connect it to the metal case that's on the outside of the device it's plugged into. Say it's an audio mixer or whatever it is, something like that. In that case, the interference flows down the shield and flows on the outside of the case. It's outside, right? But no, what do? Pin 1, which is the shield, they run it through the connector into the interior of the equipment. So now that's we call conducted radiation comes down the shield and goes right into the inside of the gear. Every amateur radio known, except for a Flex 6600, 8600, has a pin 1 problem on the microphone. So yeah, flexible, they have a little 3 millimeter jack on the back. You look at it, and by golly, the jack is screwed to the nice aluminum chassis where it should be. So the shield goes to the outside of the chassis. Every other one does it wrong. So the shield goes into the radio. So this is the standard way that you get RF on your audio. You have a intense RF field, maybe you're too close to your antenna, or maybe you didn't use a balun and your transmitted power is coming down the outside of the shield, the coax, and your whole station is hot with RF. You might even get a shock off of it or something like that. Some of the guys doing SOTA POTA, especially the POTA guys with 100 watts and these crappy antennas that we tend to use, you end up with RF, getting on the rig. Well, what happens is then it gets onto the shield of the microphone and goes into the radio, gets into the audio circuits, and every time you key it, you get this garbled, horrible, chewed up feedback because the modulation goes out to supposed to radiate, comes right back through the microphone. So that's the pin 1 problem. This isn't a problem with things like the RF connectors. Those are always properly grounded, but it can come in through an Ethernet cable, a USB cable, almost any cable, and you see it absolutely everywhere. Everywhere you look, the connector is on a circuit board peeking through a hole in the chassis. So the shield goes through the hole in the chassis into the circuit board and lights it up inside the radio. And military systems do not have this problem. Why? Because the tests we have to pass for military systems, they make very careful examinations for exactly this kind of problem. And if you have a pin 1 problem, bam, you're going to fail every single time, and that equipment will never be deployed. So we do grounding and shielding plans where the shield comes down to a connector. It's captured 360 degrees around the connector. The body of the connector goes to the outside of the enclosure, and then you will never have that problem. So that's the word on pin 1 problems.
Hi, I have a two-part question on feed lines and choking them. So I have a 50-foot feed line that's LMR 400.
Mhm.
So the first part of the question is, do you choke just the antenna feed point, the shack end? I've read some people do it 17 feet in, a certain wavelength in. Second part of the question is, with something stiff like LMR 400, is the clip-on ferrite you showed, is that the best option?
Oh, I just want to ask, what kind of antenna is this connected to?
This is a end-fed half wave.
Good old end-fed head wave. Okay, so for what it's worth, a balanced antenna like a dipole, it's very symmetrical, tends not to have these big common mode problems. It's not too much of a problem. The balun is still very helpful to have there at the feed point. An end-fed is a completely different beast. There's sort of no such thing as a real end-fed. What happens is every antenna has 2 sides. The dipole is symmetrical. Then you can feed it, off-center. Then they call it off-center fed. And eventually you make the one end really, really short, and they call it an end-fed. But there's still another half to the antenna. And the other half on many end-feds, guess what? It's the outside of your coax. That's the other half of the antenna. So you have the feed point, long wire, coax, which is the other side of the antenna headed down towards your shack. Now, if there's no choke on it, well, the entire feed line, all the way down to your radio, and you holding on the radio, you're all the other half of the antenna. Sad to say. So that means that the RF energy is present everywhere along the coax. So someone with a responsible design for an end-fed will specifically address that. Preferably they would build a choke right into the feed point transformer. It's like a 49-to-1 transformer, whatever it is. Anyway, they'll build a choke right in there so the coax is not connected to the antenna, and then you add a quote counterpoise wire, which is explicitly the other half of the antenna. Notice it's not end-fed. It's not. There's another 16 feet of wire. It's an off-center fed antenna. It's not really end-fed. Okay, but the antennas that don't have that, the coax is part of the antenna. So there needs to be a choke. Otherwise, your station's going to be hot with RF. You have all kinds of problems. So how do you choke coax? Well, there's several ways. It's possible to take things like these large clamp-ons, and you can get 4 turns of LMR 400 through one of these things. The bend radius is kind of large in LMR 400. You can get it down to about a 9-inch circle or something like that. And you can clamp these on. You can even clamp more than one onto a loop like that. The impedance is not very high when you do that. And the problem is on an end-fed, you're at the very end of an antenna. The very end of any antenna is a very high impedance point, thousands of ohms. In order for a choke to do anything, it has to be greater than thousands of ohms, preferably much greater. It's virtually impossible to build a choke that's 100,000 ohms. You can't do that. It really doesn't work. So the best we can do is attempt to put a choke partway down the feed line, or maybe put it all the way up at the top of the antenna and put on counterpoise. Maybe that'll help. You can wrap the coax through a few times and you'll get not much choking impedance. You'd be lucky to get 600-800 ohms, maybe something like that. The other way to do it is sometimes they'll sell it as a line isolator. So a line isolator is a really nice choke, wound sort of like this with coax or twisted with pairs of wires. It's in a little plastic box and it's got connectors on it. So that will be a pretty high impedance choke, 5K or something like that, hopefully, on the bands of interest. And your coax goes to the antenna, to the line isolator to the shack. Yeah, and in that case, if that doesn't solve the problem, you still got RF in the shack. You end up putting another line isolator down towards the radio, or or come up with a different antenna arrangement that doesn't have that problem.
Thank you.